Today I'll be showing you a step-by-step procedure on how to estimate an ARDL model with dummy variables using Stata. I'll be using Stata 13 for all my Stata tutorials. As usual, I always use my do file and my log files. The commands to execute for Stata have all been written out. I have steps 1 to step 7. So these are the basic steps you need to know if you want to run an ARDL model and you are including dummy variables in your specification. Number 1, you have to prep up Stata for time series analysis, then go ahead to obtain the optimal lags, after which you test for stationarity. Then you go ahead to estimate the ARDL model, perform the bounce test. The outcome of the bounce test will indicate whether you need to execute an ECM model, after which you now perform some diagnostics. So I have 7 steps for you to execute an ARDL model with dummy variables. But before we begin, let me show you what I have in my data editor. The data is on Nigeria from 1980 to 2015. You can see it here, 2015. So that means I have 36 observations. I have 3 main variables: the Gini index, domestic credit, and secondary education. And I also created a dummy variable. You must have an assumption for including the dummy variable in your model. In my own case, I'm testing for structural break. So I need to create a dummy variable to capture the break in the model. So my dummy variable is going to take 0 from 1980 to 2008. You can see it here. And it takes 1 from 2009 to 2015. There are also steps for you to know whether your model is suffering from structural break or not. So you can go ahead to watch my videos on child test and also the Gregory Hansen cointegration test for structural breaks. So those ones will help you on how to define whether your model has structural break or not. So that being said, my dummy variable here is capturing structural break in the model. So I also went ahead to interact the dummy variable with the 2 regressors, as you can see here. So in total, I'm having 5 regressors and 1 dependent variable. As I said earlier on, these are the commands already written out for Stata to execute. All these estimations have been done, so I'm going to show you the outcome from a Stata domain. Okay, so this is step 1, as you can see. Prepare Stata for time series analysis. And this is the code I gave Stata to execute, tset here, as I showed you in the do file. And here is the output from Stata. My time variable is set from 1980 to 2015. If you don't execute this command, Stata will not perform your time series analysis. Step 2, you are to obtain the optimal lags for each variable. And I have 6 variables. So this is the first one, Gini index. The command is varsoc log Gini 2. This is the way I coded my Gini index. And here is the outcome of the lag. 1 is the optimal lag. And I'll be using the Schwartz criterion for my lag selection. So it's 1. Let's look at domestic credit, varsoc LNDC. Again, the lag structure you can see here is 1. Same thing for secondary education. The lag structure is 1. Let's take a look at the dummy variables, because you have to test for that also. This is varsoc dom. The lag structure is 1. The interaction with domestic credit, the lag structure is 1. Then let's take a look at the last one. The dummy variable interacted with secondary education, the lag structure is also 1. So step 2 is done, conducting optimal lag selection. Step 3, go ahead to test for stationarity of each variable. I'm using the Dickey-Fuller test, which is the augmented Dickey-Fuller. It becomes augmented Dickey-Fuller when you make provision for the lag. If I don't put the option lag, I'm simply running the Dickey-Fuller test. So augmented Dickey-Fuller is when you include the lag. So here is the outcome for the Dickey-Fuller for the dependent variable. You can see here from the maximum p-value is clearly non-stationary. Even the test statistics also shows it's clearly non-stationary. Let's look at the domestic credit. Stationarity test for domestic credit is significant at 5%, and we can see the test statistic also is significant at 5%. You can see, in absolute terms, is higher than the 5% critical value. So Domestic credit is an IO series, it's stationary at level. Let's take a look at secondary education. From the maximum p-value is clearly non-stationary, and the test statistics also is non-stationary. It's lower than the 5% critical value. It's even lower than the 10% critical value in absolute terms. The dummy variable also is non-stationary, looking at the maximum p-value and also the test statistic. The interacted term with domestic credit is also non-stationary, looking at the test statistics and also the p-value. Same thing for the secondary education interacted with dummy variable. It's not stationary, both looking at the p-value and also the test statistic. So what we have to do is to stationarize all those variables that are non-stationary. So starting with the Gini index, all you have to do, look at this command here, dfuller d dot. So this is the first difference of the Gini index. So executing that, this is the outcome. It is now stationary in absolute terms at 1% level, and you can see here the p-value. Same thing for secondary education, d.sedu is simply taking the first difference, and by that it is stationary at 1%, and also you can see the p-value here, highly significant at 1%. Same thing for the dummy variables. You can see here, this is the first difference of the dummy variable, significant at 1%, both in test statistics and the p-value. Let's look at the interacted term with domestic credit, significant in test statistics, you can see 4.9, and also the p-value significant at 1%. Same thing goes for secondary education interacted. You can see the test statistics here, now significant at 1%, and you can also see the p-value. So step 3 is also done, testing for the unit roots of each of these variables. Step 4. Now go ahead to estimate the ARDL model. Look at the model specification here so you can adopt the same for your work. I'm using maximum lag 1, going by the result I obtained from the Schwartz criterion. So you can see the way the model is specified. This is the dependent variable. These are the two initial regressors. And you can see the dummies here. This is the dummy, and these are the interactant terms with the dummy variable. And I'm giving the option maximum lag of 1. At this spot, in Stata, Schwartz criterion is the default information criterion. So if I put AIC here, I'll be telling Stata to use the Akaike information criterion lag structure. So by not putting anything here, I'm simply telling Stata to use the default Schwartz criterion. So here is the outcome of the ARDL model. But this is not where I'm going. After you have estimated the ARDL model, you have to execute this command, matrix list elags. This matrix elags command is to obtain the actual lag structure for these variables by which you are going to use to estimate your bounds cointegration test. So by using this command, I obtained 110000 for the respective lags for the variables to be used in this model. So these are the lag structure I'm going to impute if I'm going to obtain my bounds cointegration results, or the ECM, should in case there is cointegration. So let's move on to step 5. Now perform bounds cointegration test. Remember, this is the obtained lag structure which I have now put into this place in the lag structure box. And I'm going to use the EC option and B test. If you don't put the EC option and you only put the B test, Stata will not perform your bounds cointegration test. So this is the way you must spell out your code or your syntax if you want to perform the bounds cointegration test. Executing this command, this is the results. I'll just move on straight to the bounds result. This is the result from the ARDL bounds test. You can see the F value is significant at 57.7. And what is the criteria? You reject the null hypothesis if the value of the F statistics is higher than the I1 series. You can see here, 57.7 is clearly higher, even at 1%. But if the value of the F is lower than any of the IO bounds, you cannot reject the null hypothesis. So in that instance, there is no cointegration among the variables. But from the result that we have here, there is cointegration among the variables because 57.7 is clearly higher than 4.68. Step 6. Having obtained cointegration result indicating that there is long-run convergence, you go ahead to estimate the error correction model. That is step 6. And this is the syntax for the error correction model. You can see it here on the screen. And the error correction model, you can see here model EC, is different from the one I showed you before that indicates model level. So model EC indicates error correction. You can see the option here, EC. And here is the outcome. There are now 2 compartments or 3 compartments you can see. Adjustments, long run, and short run. There's adjustment here significant at 1%, and the adjustment coefficient is also negative. So this is one of the key things you must look out for the adjustment coefficient. If it is not negative, it means there's not going to be long-run convergence. The model will be explosive. So that may depend on your research and analysis. But if there's a negative sign for the coefficient, it means there's going to be long-run convergence among the variables. It also indicates that previous errors will be corrected in the current period. In our own case, the speed of adjustment is 33.24%. So this is the outcome of my error correction analysis. So the last step will be to test for diagnostics. So let me go back to my do file. And here you can see I have already listed out the commands to use to run diagnostics. I need to know if my results can be taken seriously. I'm testing for serial correlation or autocorrelation using Watson and Bush-Godfrey. You can see that. I'm also testing for heteroscedasticity using the White test. You can see that here. Then I'll be testing for normality using the Jacobera statistic. You can see there. Lastly, I'm testing for model stability using my CUSUM. So all I need to do is just highlight all this and click the execute button. We have the Watson result here. At 1.98, it indicates there is no serial correlation. Here is the Bush-Godfrey test for autocorrelation with a statistic of 0.63. We cannot reject the null hypothesis of no serial correlation. Heteroscedasticity test using the White test. Homoscedasticity is a null hypothesis and we cannot reject that null. So this model is homoscedastic. Let's take a look at Jacobera. Our Jacobera statistic for normality test is 0.8922. So clearly we cannot reject the null hypothesis of normality. So lastly, let's take a look at the CUSUM, which is stability of the model. And here is the CUSUM graph. There's a deviation, then a reversion back to stability. It's so funny because when I use Avustain, the CUSUM graph was clearly in between the 5% boundary. So I don't know why Stata is showing me a slight digression before reverting to stability. So I will also say that this model is good. It's still okay, considering the fact that every other diagnostics gave this model a pass mark. So I will settle for this, that this model is stable, despite the slight digression, but there's a reversion back to stability. If you need the data set for this tutorial, simply click on the video description. You will see the link to the data set. And if you need my do file, you can send me a mail and I will personally send you the do file. You can send me a mail on CrunchEconometrix@gmail.com. The email address again is CrunchEconometrix@gmail.com. Thank you for staying with me. Hope to see you next time.